Greetings. This talk is on NIM in an RTOS world. My name is Jaremy Creechley, and I've been using NIM in embedded context for about a year now, and wanted to give a presentation on some of the things I've learned and some of the discoveries I've made. And to start out with, embedded programming is an interesting area, and it's a little bit difficult to program. Most of the tools are actually still from the 90s era, and often for good reason. It's difficult to set up a build chain, and the tools are often from vendors of the CPUs themselves, and they vary in quality and documentation, support, and a lot of other points. So there's a lot of variability in the embedded world, and that makes it actually fairly difficult. And a lot of the challenges are that programming in the embedded world often requires deterministic programming. You want the action to happen within a certain predefined amount of time, and or to be able to interrupt and handle tasks that are higher priority pretty immediately. Um, the MCUs that they run on are often much smaller or have less RAM and or flash memory than desktop computers. And especially about a decade ago or more, it was very difficult to find more than a few kilobytes RAMs on many common microprocessor units. Now, many microprocessors have tens or hundreds of kilobytes of RAM, which means that the old tools aren't quite keeping up. When you start needing to deal with hundreds of kilobytes of memory, it becomes much more difficult to make a C program that doesn't run into constant errors. Now, on an MCU, you don't always have memory protection. So that means that it can corrupt the entire microcontroller environment and lead to crashes. So I've been always kind of curious about whether alternatives could exist out there, and I've been looking for a long time. I went through a lot of loops and finally landed on NIM. But first, a couple of the languages out there and a couple of the tools that are already in usage. So assembly language is sometimes still fairly popular. There's some TI processors and PIC processors that still have a lot of assembly out there. And for some cases, that's all you need. If you need a really, really inexpensive 8-bit microprocessor that does a very simple timing task, then a few dozen lines of assembly code suffices. Now, C is by and far the market leader. It's pretty much everywhere. All the tool vendors use C or some version of C, and essentially most of the microprocessor board support packages and RTOSs are generally programmed in C. There's also a fairly big subset of C++ with variations. Many C++ variations in embedded world don't have exceptions or don't allow RAII management. Some may or may not support the newer C++ 11 or 14 or 20 standards. Another one, and I actually kind of enjoyed ADA, but I've never used it, is ADA. So it was designed for the DoD back in the 80s and gained actually some amount of success, and unfortunately just never broken out of a few niche communities. It is still very widely used in some of those communities, and it provides an interesting feature set where the compiler can automatically detect certain classes of errors. And it's largely based on Pascal and very verbose from the code snippets I've read, and unfortunately has a very limited open source community, which makes it a little bit difficult. I love open source communities, and being able to get a lot of people to share code and wisdom really, I think, is important for modern programming language. Finally is Rust, which is a new contender a lot of people know about. It's actually really fantastic. It's memory safe, but it is also heavy and complicated. It relies on LLVM, So it's not available in all microprocessors. It's also a little bit more difficult to integrate into existing compiler tool chains and RTOSs. A lot of RTOSs have either their own build system or they require CMake or GCC, and often their version of that. So having a language that is really only able to work with LLVM and Clang means that you essentially have to recreate the entire board support package and all of the details of the hardware. And there's some fantastic communities out there doing that. However, I wanted something that I could hit the ground running with and make use of the existing RTOSs out there and a lot of the driver code and everything without having to interface with Rust. So I eventually ended up deciding to try Nim, and I think Nim has a lot of great properties for usage in the embedded context. So it's a high level language and semantics, but it also provides great low level bit fiddling and pointers. In the standard library, there's pretty much everything you would need to deal with addresses and pointers, bit munging, and all the other standard things alongside some features you wouldn't find in C. Um, Nim also has a powerful garbage collector, and you can also do manual memory management pretty easily. There's no equivalent of a safe or unsafe keyword as in Rust. And so you need to be careful with your code. But generally, when you're wrapping existing C code and C libraries, you end up dealing to some degree with pointers into their libraries, and being able to manage those and wrap them in a safer Nim constructs is really helpful, really handy. Now, Nim compiles to C or C++, and also Objective-C and JavaScript. For the context embedded, generally, I've mentioned C and C++. It's great because it will compile and be able to integrate with existing code bases out there, which is great for most RTOSs, which again are generally in C or C++. Nim also has a fairly simple foreign function interface, since it actually is code compiled into C or C++. It literally has no overhead. There is, well, actually, there is some overhead in string handling and things like that, where Nim will provide a length and some safety features. And it gets a little strange to convert between those at times. But overall, it's pretty seamless, and you can go back and forth pretty easily. Now, the other question is Nim worth the effort over C? If you can just take C and take your existing RTOS and embedded system and just program in C, what benefits would you gain from Nim? A new compiler, you know, with Nim, you have to pull in a new compiler, you have to learn a new language and new libraries, and that's a fair bit of work. So I think some of the best things for Nim that I found were that's a simple language. It looks enough like Python that generally most programmers can grok it on first glance. There's a few catches, but not too many. It has built-in async support. My favorite are the hygienic macros, which in C you often end up doing a lot of really gross macro munging and just trying to get the text-based substitution macros to work in C and auto-define certain properties or registers. And with Nim, you can actually do that at compile time in Nim. It's much cleaner, much nicer, and also much easier to use in C++ constant expressions, which are finally being supported, I believe, in C++ 20. Now, Nim also has a very flexible standard library. It's fairly hackable. So I found I was able to pull open the Nim compiler code base and standard library code base, and I was able to tweak it and tweak the memory handling, tweak how things are allocated if I wanted to. You can swap to a memory mapped region or a area that is just hard coded to pull up, or you can use system malloc, or you can write your own and a few dozen lines of nim, and generally it just works. It's also convenient that the compiler is really small. It's only about 4 MB on my system, compared to a full LLVM-based compiler, which can be 100 to 100 MB. Now, on the right down here, you can see that I have a snippet of nim code with a macro, to look up table, and it goes through some string that is given at compile time. It's a constant. It will be able to parse it and split it up into a table that is compiled and set up at compile time. That can actually be very useful for embedded context where you want to have some pre-processed code, but you don't want to do it at runtime. You want to be able to use that compile time code to be able to simply set up some data structures without having to have it occur at runtime. Now, one of the other big things that brought me to Nim, and why I think Nim is a very great, an ideal language in many ways for embedded, is its new garbage collector. So Arc came with Nim 1.4, if I believe correctly, or is now default in Nim 1.4. It's a rather unique garbage collector where I'd say the whole is greater than the sum of the parts. For example, its reference counting is its essential mechanism, but they've integrated move semantics into that. And it's one of those things where it sounds fairly simple up front, but once you start digging into it, exposes a lot of power, and also makes it very useful in both terms of performance, but also small size and determinism, among other things. So the move semantics allow the reference counting system to assume that only one thread is going to increment or decrement the reference counting at during execution. This means you can drop the atomic counters and locks, which are prohibitively slow in a lot of programs, and something you would not want to have occur a lot during a real-time operation, interrupts and things like that. And so it's great to be able to remove those from the system without having to have a pause the world, tracing garbage collector, or other mechanism. By using the move semantic, you can also essentially get unique pointers, kind of similar to the C++ unique pointers, where you can ensure that a graph is only connected by one pointer that you can then shift to another thread or context. And with that, you can actually avoid copying data between threads while still being able to synchronize and use your reference counting as if it was on a single threaded device. So that results in a minimal amount of memory overhead. Again, it's just a integer, a short little integer. It's deterministic. So if you run the code multiple times, you reboot the embedded controller, it will come up often with the same pointers, the same memory allocations, everything like that. And it's very easy to predict when and where things will be both allocated and deallocated, which is very helpful on the embedded context. I'll get into that a little bit later. And especially it has no pause the world features. So if you have a global variable and it has a complex table or other collection in it, and you have an interrupt function that runs, with a little bit of work, you can ensure that it's not going to pause the world or trigger a garbage collection cycle, or a number of other things that would cause your interrupt to behave poorly. And often that can actually result in a crashed RTOS or other, it can cause other issues on the microprocessor. Now, another nice thing is it achieves this without using the manual lifetime annotations like you get in Rust, which is nice. A lot of times you just want a simple program and you don't care too much about the exact details or performance. And, in general, probably 80% of the embedded code I've used, the exact performance doesn't matter, or exactly when things get allocated or deallocated don't matter. So most of the time, I just want something simple to use and program. And I believe Nim brings all that, and especially with that new Arc garbage collector. And you can also run it with Arc, which is purely a reference counting system. It does not detect cycles or anything. And if you program with standard collections and you are careful not to introduce cycles, then that is fine. Now, you can also run it with a cycle collector, and that takes a little bit more care that you don't actually go back to a pause the world scenario. But that one's also good in that it's limited, it's still very fast, and again, it's optional. You can choose to use it or not to use it. So a big thing has been what is the experience of Nim in actual embedded work? A lot of times you look into a language, it sounds great, but once you start using it, there's just so many little paper cuts that it isn't worth the effort, or it becomes more hassle than it is worth. So initially, I tried writing a little example tool on an ESP32 using Nim, and I was surprised it worked. I think I tried an Arduino sketch first, just a board I had laying around. There's fairly limited functionality at the time. It didn't quite support a lot of the more useful things, the free RTOS and LWIP from the ESP IDF library. And so I spent a couple of evening and weekends working on it, kind of a fun side project, and also useful to determine if it would be something good to rewrite my firmware in. And after a couple of weeks and being pretty much a newbie to Nim, I got a PR pull request in on GitHub, and thankfully it was reviewed pretty quickly, and the team accepted it. So it was mostly a few modifications to the Nim support for POSIX to support a few of the oddities in LWIP. Now, the nice thing is that free RTOS and LWIP should be able to be supported on quite a number of existing RTOS implementations. TI, well, actually, I don't know if it's TI. Let me back up and say a lot of the Amazon web examples, IoT examples, and their systems actually rely on free RTOS and LWIP. So it should be able to plug into those systems well and natively understand LWIP using standard Nim tools, sockets, libraries, and other features. So again, it's a little tricky because there are some areas of POSIX which Nim supports, like files and things that aren't generally included by default in real-time operating systems. So when you get to those areas, Nim may let you try to compile code, but you'll probably get compilation errors. And so you really kind of will be going off onto a deep end there. So if you want to, you can make it work. And I believe there was a pull request I had on one of the projects where someone was supporting some of the Flash or FAT32. So it is possible, but you have to kind of dive into it yourself and be willing to explore and fiddle the low-level bits. So creating a wrapper for an RTS really isn't that complicated, not really more so complicated than wrapping a complex C or C++ library, especially if it is similar enough to free RTOS, or you're not using a lot of things like trying to wrap a file system. For example, I eventually decided to write a wrapper for the ESP32 ecosystem, particularly the ESP IDF, which is their RTOS fork that they have tweaked, and they've done actually a really great job of creating a open source community. There's a lot of pull request issues, and generally the development is all done on GitHub out in the open. And the ESP32 chips do provide a lot of functionality. So I figured it'd be a good place to start wrapping a RTOS with. And again, with the previous free RTOS and LWIP, it was actually pretty easy to begin wrapping the core APIs in the ESP IDF system. ESP IDF is open source, it's a CMake build system, and so I was able to integrate NIM into that fairly readily. On the right here, you can see an example of some code. And so I've done a little bit of experimentation with exactly how much of the original C format to keep and how much of it to uh, put into a NIM wrapper. And going between things of, do I use camel case or snake case? I've generally kind of used snake case to infer C and C++ code while using um, camel case for NIM code. And I may have said that wrong, but it's using snake case for C and C++ code, which often the ESP IDF library uses, and then using camel case for NIM or NIM wrapper code, which is more of a preference thing. Different people like in different ways. You can see though, I was able to wrap the GPIO thing libraries in using NIM sets and doing a few other tricks to try to make it a little easier to uh, come up and initiate a GPIO pin or configure it, and without having to worry that you got it implemented correctly. And see, there's a lot of boilerplate code. And oftentimes, if you're copying an example, you have to actually dig into it. You have to create a struct, and then from that, you have to initialize it, and then you have to check that it's correct. And the NIM wrapper code can handle all that and then throw an exception if something goes wrong. So that makes it a little easier to just have code that works on a happy path. And if you need to, you can catch or dive into errors. So eventually I decided to rewrite my sensor firmware in NIM, and it ended up being only about 4,000 lines of NIM and using the Nesper library that I created. And it turned out pretty well. You can see some of the comments I had down there. I didn't really write that much many lines of code, but it's an artifact that at some point I decided to check in all of the generated NIM code and generated ESP IDF code, which probably is not a good idea if you don't want to really balloon the number of um, uh, the number of lines of codes you're changing. I did run into a few corner cases, especially early on. NIM with ARC was still relatively new. There was nothing that I think was a real big showstopper. A lot of it was either documentation or figuring out how multi-threading would work before ARC officially supported multi-threading. And I know there's still a little bit of work in multi-threading and just updating the libraries to fully take advantage of ARC. But by and large, everything just worked, especially in pure NIM code. It generally worked fine, and it saved a lot of effort. So 4,000 lines of code would probably be more like 10 or maybe 15,000 lines of C code, just due to the amount of boilerplate you'd have to do, especially if you're trying to do JSON type of things or message back in my case, um, or remote procedure calls or anything like that. Generally, it become very verbose and take up a lot of lines of code in C. Now, I learned a few lessons working with NIM on the ESP IDF, and hopefully things that will apply to other RTOSs. I found that NIM can use its own build system, but I found it easier just to integrate with the MCU's build system. I eventually added support into Nesper that will add a nimble task that will do all the right calls into the build system, particularly the ESP IDF, and it'll call the reconfigure functions, it'll update and inform it to automatically update the NIM code and recompile it. Generally, using the caching in the ESP IDF CMake system, it's actually pretty fast to do a full rebuild of the NIM code, which takes maybe a second or two. And then the final linking and rebuilding of the C portions, which only take about 20 seconds or so, because most of the system has already been built up and cached. And that means that you don't have to do rework any of the uploading, any of the details on handling the semantics of the Flash system, which is a whole area that you can get lost in. And so it's nice to be able to reuse those RTO systems, their build systems as they are. So another thing I did find though is that the malloc in RTOSs can be a little bit finicky, uh, depending on race conditions or other things. They seem to be not as well tested or often well used on real-time and operating systems. Likely just because real-time or dynamic memory used to be very frowned upon in microcontrollers, and in some scenarios still is, especially if you need a piece of code that is very deterministic. Again, NIM can support that nicely by essentially pre-allocating code during boot up, or if you really need to, you could create your own static allocating cache or arena or something like that. The benefit of NIM is that outside of those areas, you can also fully utilize a garbage collection and use all of NIM's collections, sequences, tables, filters. You can use the iterators. It has great JSON support built in. And a lot of the JSON support in embedded context is very painful, but it's also very nice for just a very simple message system, especially if you're working with others or trying to show them a very simple, utility. And it's generally much more secure and easier to use in the C or C++ equivalents. And you're less likely to shoot yourself in the foot. Now, NIM with multitasking is a little bit interesting. It's still an active area of development, I believe, but it still works surprisingly well, given that it was not officially supported when I began working with it. I was able to either use some of the existing NIM utilities. Um, uh, Channels worked pretty well, uh, but they were fairly inefficient. So I ended up generally using the free RTOS XQs and X signals that ESP IDF relies upon. And likewise with other RTOS systems, you should be able to use their system. The move semantics, especially with a manual move annotation, is actually very powerful. Like you can specify to the compiler that you are moving a piece of code to another thread. And it's only a few characters. And generally, again, just seems to work. Arc integrates well with that. And even the interrupts, you can interact with it. Generally, for anything that's more interrupt based, I was using globals. And so I just wanted to be sure to not need to allocate or deallocate the memory for that. And so as long as the global always exists, it should never get down to where it deallocates. There could be some issues where if you're not careful with which thread or which interrupt is using it, where the it could get corrupted. So far, I haven't run into that scenario. Generally, I will configure a piece of memory or a global variable and then only use it from a specific context. But that could be something that could be error prone. And I believe NIM has some tools and some proposals in the works that could actually help with that. Now, even though NIM helps a lot with some of the trickier areas of RTOS programming, there's still a lot of challenges. The RTOSs seem to be very buggy. ESP IDF definitely have their own set of bugginess and issues. Some drivers on some chips don't work, or sometimes the timing on the I2C is off. The UART driver is a little frustrating at times. And a lot of that is just it seems to be fairly common in RTOS world. Some vendors are probably a little bit better, and if you're going with commercial vendor, perhaps some of those areas would be uh, a little easier. However, NIM doesn't really wrap the board support packages or anything like that. So likely you're going to still be dealing with some of those issues, which is both a pro and a con. I have thought about at some point of what it would take to write a NIM native RTOS type of system. But again, you're back to supporting the quirks of hardware and ensuring that works well. And again, to reiterate, the dynamic memory subsystem can still be a little bit tricky. So if you're creating a lot of garbage, and you might want to minimize that. So there are some things I ran into with JSON, where I was creating a big array of integers, and eventually I ended up doing a couple little hacks around that just to avoid making 10,000 little JSON wrappers that were instantiated and then freed really quickly. It's pretty inefficient, but again, those areas are something that NIM provides the flexibility that you can work around if needed. And maybe it's still one of the downsides is that you still need a fairly good working knowledge of C to really delve into an RTOS system at this point with NIM. Um, Not 100%, but it really is helpful if you want to do any kind of serious, larger projects. Um, However, it would also be a good way to learn. So if you started with a simpler project with NIM, you can look at the generated C. It's a little painful, but still doable. You can actually see, you can use the GDB debuggers and work through those different aspects and often follow the documentation. Really, at the end of the day, all you need to be able to do is know enough C to be able to follow the RTOS documentation on how to create certain drivers or allocate things and how to initialize the system. So future directions, I think it'd be great to see a Zephyr port for NIM, which would be fantastic. Zephyr is gaining a lot of popularity. It's supported by a couple of big chip vendors, NXP in particular, and a couple of others. And it actually has a much larger community. So it's kind of similar to ESP-IDF in that it has an open source community. There's a lot more rigor around testing and bringing more modern software development tools and practices and processes to the RTOS world. So I think NIM and Zephyr would actually be a great combination. My work has actually been pretty busy. I've actually used NIM on a couple of projects, and but at some point I'm hoping to be able to follow up with that. At some point, we'll probably try to create a embedded NIM GitHub organization and try to gather some of these. I know there's some great NIM tools for the original ESP chips. I forget the name, 2866, and Arduino code. And there's some real exciting potential in being able to use Dr. NIM to provide ADA-like and Spark-like formal verification, especially for key portions of NIM, such as the semaphores, queues, and also driver interrupt timings. So being able to lock devices and ensure that you never run into a case where you have a deadlock or other issue due to multi-threading. So thank you for listening to this talk. Hopefully it was interesting. I apologize for the quality of the audio, and it's kind of a last minute talk here, but hopefully you're see a little bit of excitement on using NIM in an embedded world, and we'll give it a try. All right, thank you. Night.